A medical research team studied the ages of the patients who had strokes caused by stress. The ages of 34 patients who suffered stress strokes were as follows. Take a minute, enter the 34 numbers into your calculator, run the 1-bar stat test. I'll put mine up on the screen in a moment, and we'll see if we are in agreement. So here is what your average should have been. Always check to make sure you have the correct number of numbers. The question said there's 34 patients, so our N is 34. And here the average is a little under 47. Now we have to calculate the 5-number summary, and the 5-number summary are the last 5 values that are listed here. So the minimum is 28. The lower quartile, that's 36. The median, 45.5. The upper quartile, that's 57. And the maximum is 97. So that's our 5-number summary. And we're going to construct now a box and whisker plot. And we're going to construct this box and whisker plot, as it says, to scale. So we're going to press second and Y equals to go to our stat plots. The box and whisker plot is the 5th type of graph that you see, or for those of you using the older versions of the calculator, the bottom middle type. Make sure the X list matches the list in which you entered your data. And now we're going to press zoom and go down to option 9 for zoom stats. So here's what our box and whisker plot looks like. By pressing trace, the cursor pops up and tells you the median is 45.5. So what we're going to do is we're going to construct that on this number line. We know our values run from 28 to 97, so maybe what I'll do is I'll break up my number line by 20s. And we're going to draw this thing to scale, so we're going to make each 20 interval look correct. Here our minimum is 28. Our lower quartile is 36. Median 45.5. Upper quartile 57, and the max of 97. So here is our box and whisker plot, and if you notice, it is drawn to scale. Next, we're going to calculate the interquartile range, the IQ or the IQR. We're going to take the upper quartile Q3 minus Q1. Here, our upper quartile was 57, our lower quartile was 36. So here when we go 57 minus 36, our interquartile range is 21. What we next need to do is calculate the lower fence and the upper fence for the data. And the lower fence and the upper fence are the boundaries for outliers. We want to come up with a range that is considered quote-unquote normal, and any values outside of that range are considered outliers. And here are the formulas you want to know. The lower fence equals the lower quartile Q1 minus 1.5 times the interquartile range. The upper fence is the upper quartile Q3 plus 1.5 times the interquartile range. So here our lower fence is equal to Q1, which in this case was 36, minus 1.5 times the interquartile range, so minus 1.5 times 21. So here our lower fence turns out to be 4.5. So that's our lower fence value. The upper fence, that's equal to the upper quartile Q3 plus 1.5 times the IQ, or the interquartile range. So here our upper quartile was 57, plus 1.5 times the interquartile range, so plus 1.5 times 21. So here the upper fence turns out to be 88.5. So what does that mean? Basically, any data value that's not in between these two fences. So here our fences are 4.5 and 88.5. Any number that's not in this range is considered to be an outlier. And if you look at your data, the number 97 is outside of this range. So the number 97 is considered to be an outlier. Now, one way you can confirm that that 97 was an outlier was to construct a modified box plot on your calculator. If you go to your stat plots, again, second and y equals, the modified box plot is the fourth type, or for the people with the older calculators, the bottom row first type. Make sure your X list matches the list in which you entered your data. And then once again, go to Zoom Stat. Here's what your modified box plot looks like. If you press Trace, you can move the cursor all the way out and see that this point out here was that outlier of 97. So we're going to have to construct a modified box plot, once again drawn to scale. So I'll break my number line up by 20s, as long as you choose a consistent interval. So here's what our modified box plot looks like on the calculator, and we'll draw it like this. It does have to resemble the graph on the calculator, and I just chose to go up by 10s to show you that it doesn't matter as long as you stay consistent. The next part of the problem has you identifying the percent of the data that lies within 2 standard deviations of the mean. So we're going to have to go back to our 1-var stat test and get the mean and the standard deviation. Here our mean, our x bar, if we go to the nearest tenth, this 7 kicks that 9 up to 0, makes the 6 go to 7. So here our mean is 47.0. And for standard deviation, we're always going to use the value that's above the n in this class. So in this case, our sigma, our standard deviation, is going to be 13.6. So what we're going to do is we're going to go 2 standard deviations away from the mean. We'll kind of imagine a number line. We'll put the mean, the average, 47 in the middle. And here we're going to go 2 of these, so 2 13.6s in each direction. So basically what we're going to have to do is we're going to have to add 2 times 13.6 and subtract 2 times 13.6 from the average. So when I do this on my calculator, I take the average of 47 and add 2 times 13.6, take the average 47 and subtract 2 times 13.6. We're doing 2 standard deviations because that's what the question says. So here basically we have a range. We have a range from 19.8 to 74.2. So we want to know what percent of the data lies within. I want to know what percent of our numbers are in between 19.8 and 74.2. So what you're really going to want to do is to put your numbers in order and then count up how many are in that range. So let's first sort the data in order. We do that by pressing the Stat button and going down to option 2 for sort in ascending order. You're brought to the home screen of the calculator. Make sure you tell your calculator the list that you used for your data. Remember, the way you access the lists is you press the second button, and number 1 is list 1, number 2 is list 2, all the way through list 6. Press enter. And when you go back to your list of data, stat, and then choose edit, you'll see the numbers are sorted in order. Here I scrolled to the end of the list. I saw that from my 1var stat test, I know the minimum data value is 28. So 28 is going to be in between 19.8 and 74.2. It looks like the only number which is not in this range, any number that's not in between 19.8 and 74.2, that's this number 97, that outlier. So here we know that 33 of the 34 numbers are within one standard deviation of the mean. And if we divide that on our calculator, go 33 divided by 34, that's going to give us 0.9705. So if I move the decimal point 2 places to the right, that's going to be 97 point, and the 5 kicks the 0 up to 1. So here, 97.1% of the data lies within 2 standard deviations of the mean. And this is a percent, so 97.1%. Next up, we're going to calculate the 5% trimmed mean for the data. So the first thing we're going to do is we're going to calculate 5% of the number of numbers. In this case, the number of numbers was 34, so we're going to do 5%, so that's going to be 0.05. Others times, and the number of numbers we said was 34. When we do this on our calculator, we're going to get 1.7. We're going to round the 1.7 to 2. So what we're going to do now is we're going to drop the top 2 and the bottom 2 values in our list. So that's why it was very, very important that we sorted the data in that previous step. When you go back to your list, the 2 biggest values are 97 and 62. The 2 smallest values are 28 and 29. What we're going to do is we're going to move the cursor over these values and press the delete button. So basically, if we started off with 34 values, and we dropped the top and the bottom 2, we've dropped 4 values, we should now be left with the middle 30 values. And what we're going to do is we're going to calculate the mean, the average of those new 30 numbers. So we're going to go back to our 1var stat test. We're going to rerun the average. Notice again, here is the key. The n value is 30 because we started off with 34 and we dropped the top and the bottom 2. So here we're trying to find a trimmed mean, so I want to know what the average is. So here the x bar to the nearest tenth, 46.0. So that's our 5% trimmed mean for the data.
For part H, we have to use the original data, so we need to bring back the 2 low values that we omitted and the 2 highest values that we omitted when we found the trimmed mean. And what we need to do is we need to come up with a stem and leaf plot for the data. So make sure you brought back the 28, the 29, the 62, and the 97. All you need to do is go into your list, and if you press second and then delete, that's how you insert a value into a list. So insert those 4 values back in. Now remember for a stem and leaf diagram that leaves must be only single digits. You can only have single digits for the leaves. So basically the stems are going to be every digit other than the last. Now here we're dealing with 2-digit numbers, so our stems are going to be, in this case, 2, because we have 2 numbers in the 20s, 3, because we have numbers in the 30s, 4, 5, 6. Now, even though there are no leaves in the 70s or 80s, for a stem and leaf diagram, you need to include missing stems. So I need to include the stems of 7 and 8 to get to the last number 9 for the 97. If there would have been a large break, if you would have had a stem of 7 and then not again until 26, what you could do is you could always indicate a major break in the stem by using a squiggly line. So if your stems went 1 through 6 and then the next stem was 27, you can simply draw a squiggly line to indicate that there's a large break before you get to your next stem. But here that wasn't necessary. Now it's very important to sort the data in order to be able to set up a stem and leaf diagram. And your leaves must be in ascending order. So for example, I have the numbers 28 and 29, so I'm going to have leaves of 8 and 9 for the stem of 2. For the stem of 3, I have a 0 for 30. I have 2 32, so I need to indicate that by writing the number 2 twice in the leaf column. I have 4 36s, so I need 4 leaves of 6. And then I have 2 38s. For the stem of 40, I have 3 40s, so I need 3 zeros, a 41, 2 45s, 2 46s, and a 47. For the leaves for the stem of 5, I have 3 50s, so I have 3 zeros, a 55, 56, 57, and 2 58s. For 60, I need a 0, 3 1s, and a 2. And then for the stem of 9, I need a leaf of 7. We're not going to write anything next to the 7 or 8. If you put a 0 here, that means that there's a data value that's 70, and that's not true for this question. So you just want to leave those leaves for the stems of 7 and 8 blank. And the last thing we need to do is we need to write a key to tell the reader what these values represent. And the key is always the smallest or largest data value that's given. So we're either going to use the 28 or the 97. It doesn't matter. So I could write 2, then a line, then 8, and that means the number 28. Or I could have written 9/7 means 97. You don't write them both, you write either or, and it must be the smallest or largest data value. Next, we need to set up a frequency distribution and a histogram for the original data, and the question will tell you the number of intervals. So here we need to use 5 intervals. Sometimes the intervals are known as the classes. So what we're going to do is this. The first interval always starts off with the minimum value. So I reproduce the 5-number summary down here, and our minimum value is 28. And now what we need to do is figure out the size of each interval, what we call the class width. And what we're going to do is we're going to take the range of the data, and we're going to divide it by the number of intervals, the number of classes that the question tells you to use. So here our range, the max minus the min, 97 minus 28, so that's going to be 69. And we're going to divide that by the number of intervals, which they tell you always in the question, which is 5. So here when we take 69 divided by 5, and here we're left with 13.8. Now, what we always have to do is you always have to round up to get your class width. And you have to round up accordingly. What does that mean? Well, if you look at your original data was given as integers. We had the whole numbers. So basically what we're going to do is we're going to take the 13.8 and we're going to round up. You always round up. And here our next integer, that's going to be 14. So that's what our class width is. That's what our interval size is going to be. It's going to be 14. What I'm going to do is I'm going to keep taking that 14 value and add it to my starting interval point, which was 28. So here when I take 28 plus 14, I get 42. plus 1456, plus 1470, plus 1484. My intervals are now going to be set up. And what I'm going to do now is work backwards. Since my second interval starts at 42, my first interval has to end at 41. The third one starts at 56, so my second interval ends at 55. So I'm now going to set up the ending points for my intervals, and you notice you're basically just adding 14 again. 41 plus 14, 55, plus 14 plus 14, which means the last interval is going to end at 83 plus 14, or 97. So that's what my intervals look like for this frequency distribution. And now I'm going to go back to my stat plots, second and then y equals, and I'm going to set up a histogram, which is the third type of graph that resembles a bar graph. And this is the only type of graph where we're not going to be allowed to press zoom stat. Instead, what we're going to have to do is we're going to have to press the window button and set up the viewing window that matches the intervals that we've established. So after pressing the window button, this is the viewing window that we need to establish. Here, the x-min is going to be 28 because that's the smallest data value. It's the starting point of the first interval. Here, x-max, we're going to manually type in 97 because that's the ending point of the last interval. Here, the x-scale is 14 because that's what the class width was. That was the size of the interval that we established by taking the range and dividing it by the number of intervals that were given to us. The y-min is always going to be 0. The y-max, what I tell my students to do is always take the total number of data and just divide it in half. So here, since we were given 34, I did 34 divided by 2 to get 17. And for a y scale, I put 5, because what's going to happen is I'm going to set up a histogram, and on the y-axis, I'm going to go all the way up to 17, and then a y scale of 5 will put a mark at every 5. So you'll be able to see the 5, the 10, and the 15 points along the y-axis. So after pressing the window button and setting up this viewing window, you now must press the graph button to produce your histogram. So here's what our histogram looks like. And if you press the trace button, your calculator will now begin telling you the frequencies. So in this case, the frequency of the first interval from 28 to 41 is going to be 15. If you press to the right, it tells you that the second interval, the frequency is 9. The third interval, the frequency is 9. The fourth interval is 0. And the fifth interval, the frequency is 1. So that's how we set up a frequency distribution and histogram on our calculator. Next, we want to set up a relative frequency distribution. And a relative frequency distribution is a column that gives the percent of the data in each interval. So we're going to recall each interval and the frequencies, and now what we're going to do is figure out the percent of the data that occur in each interval. And what you need to do is have the total number of data as your denominator. So for example, the frequency of the first interval was 15, so the percentage of the data that's in that interval is going to be 15 divided by 34. So 15 over 34 as a decimal is going to be 0.44. So that means approximately 44% of the data is in the first interval. The second interval, its frequency is 9, so if I do 9 divided by 34, here I get 0.26. So that means approximately 26% of the data is in the second interval. So all you do to get your relative frequency column is you just divide each frequency by the total number of data. Here our last interval, 0.029, so 0.03. What we want to now do is set up a relative frequency histogram, which is the picture version of this relative frequency distribution that we just established. So here the biggest relative frequency I see is 0.44. So maybe what I'll do is on the y-axis I'll go up to 0.5, and then I'll break up the y-axis into intervals of 1/10. So here's my y-axis. Here the x-axis is going to be the starting points of each interval. So here I have 5 intervals, so I'll break the bottom up into 5 even parts. The first interval starts at 28, so I'll label the bottom left-hand corner as 28, and then I'll label the lower class limits, the starting point of each interval. So here the first interval, the relative frequency is 44%, so I'll go up to 44%, and I'll draw that section. The second and third interval, the relative frequencies are 0.26, so I'll go up to in between 0.2 and 3. The third interval, the relative frequency is 0 because the frequency was 0. And then the last interval was 0.3, so I'll draw that last section. So this is what it means when it says you must label your x and y axis accordingly. Next, we have to set up a cumulative frequency distribution and a cumulative frequency histogram. And the cumulative frequency is basically just a running total of how many data values you have up to and including that interval. So for example, the first interval's frequency is 15, so we're just going to copy over the frequency into the cumulative frequency. But the second interval, its cumulative frequency, its running total is 15 plus 9, or 24. So up to and including that second interval, the running total is 24. The third interval, its running total is 15 plus 9 plus 9, or 33. The fourth interval, its running total is 15 plus 9 plus 9 plus 0, or also 33. And then the last interval, its running total, 15 plus 9 plus 9 plus 0 plus 1, that's going to give us 34. And that's significant because that's the total number of data. You know if you set this problem up correctly, if the sum of the frequency column and the last value in the cumulative column are the total number of data that were given to you. And now to set up our cumulative frequency histogram, we're going to take our total number of data, 34. So maybe what I'll do is I'll go up to 40 on the y-axis, because that's an easy number to work with. I'll break the y-axis up into tens. Just like I did before, now I'm going to establish the y-axis as the total and the x-axis as the intervals. So I'll break the bottom up into 5. The starting point of the first interval goes by the origin, so that's 28. And now the starting point of each interval, the lower class limits, get labeled on the x-axis. So now I'll set up my cumulative frequency histogram. The first interval's cumulative frequency is 15, so I'll go up to 15 for the first interval. Then I'm up to 24. Then 33. I'm going to stay at 33 because there's no numbers in that fourth interval, and then I'm going to get up to 34 for the last interval. So the cumulative frequency histogram always looks like a staircase that are going upward because it's a running total of the data. In part L, we have to find some percentiles. So for number 1, we have to find the percentile rank of the data value 41. So what we're going to do is we're going to take the number of data that are less than 41, and then we're going to add 1/2 times the number of 41s in our data set, and then we'll divide that by the total number of data. and I know the total number of data given to us was 34, so that's going to be our denominator. So what we're going to do is we're going to count up the number of data that are less than 41. So we'll just count up all these numbers. And the most efficient way to do that is just to find 41 in your list. Here 41 is in the 15th spot, so that means there has to be 14 data values that are less than 41. So we're going to go 14 plus 1/2 times. Now there's a lot of different formulas that you can use to find percentile rank. This is the one that we're using, but if you get to college you might see a different formula that's given to find percentile rank, but this is one of the acceptable ones. So we're going to go 14 plus 1/2 times. Now, how many 41s are there in our list? In this case, there's 1. So we're going to do, to find the percentile rank, 14 plus 1/2 times 1 divided by 34. Here we're going to get 0.426, which would be the 42.6% if we're dealing with percentage, but we're not. We're dealing with percentile. So what you always have to do for percentile is you have to round up. So here, the answer is going to be 43. So the 43rd percentile. That's the value, number 41. Here, to find the percentile rank of 50, now we're going to find the number of data, not less than 41, but now number of data less than 50. So since you notice there's a few 50s in our list, go and highlight the first number 50 in your column. Here, the first 50 is in the 21st spot, which means the number of data less is going to be 20. So we're going to do the number of data less than 50, which is 20, plus 1/2 times the number of 50s, which in this case there are 3. So we're going to go 20 plus 1/2 times 3, and then we'll divide by the total number of data, which is 34. So we'll do on our calculator this expression. That's going to give us 0.632, which would be in traditional percentages like 63.2%, but we're not dealing with percentages, we're dealing with percentiles. So you're going to round up to the 64th percentile. Notice how I'm not writing my answers as percentages, but rather the 43rd percentile, the 64th percentile, because even though they sound alike, percentage and percentile are two different mathematical values. Now we need to figure out at number 3 which data value corresponds to the 27th percentile. And what we're going to do to figure out which data value, which of these numbers in the list corresponds to the 27th percentile, what we're going to do is we're going to take the percentile that's given, we're going to divide it by 100, and then multiply it by the number of data. This is how you find a value at a particular percentile. So here, the question says, what is the data value at the 27th percentile? So we're going to do 27 over 100 times the number of data, which in this case was 34. So we're going to do 27 over 100 times 34 on our calculator. When we do that on our calculator and then convert it into a decimal, we're left with 9.18. We're going to round up to 10. So what does that mean? Is our answer 10? No. That means the 10th number in our list, provided your list is sorted in ascending order, the 10th number in the list is the data value that corresponds to the 27th percentile. So here the 10th number in our list is the number 38 because it's in the 10th spot. So which data value corresponds to the 27th percentile? Here it's the data value 38. So our answer is 38. Finally, we need to find the data value that corresponds to the 4th decile. And deciles basically break the data up into groups of 10. So the 4th decile will be the same as the 40th percentile. deciles break the data up into groups of 10. So the first decile would be the 10th percentile. The second decile would be the 20th percentile. The third decile, the third decile, 30th percentile. So basically what we're going to do is just do what we did before for number 3 for the fourth decile. Here the fourth decile is the same as the 40th percentile. So we'll do percentile, which in this case is 40, divide that by 100, and then multiply it by the number of data values. So here we're going to do 40 over 100 times 34. So here we're going to be left with, when we convert it to a decimal, 13.6. We're going to round up to 14. So that means the 14th number in the list. So here when you go to your list and find the 14th number, that is the number 40. So the number 40 corresponds to the fourth decile.